Hi, welcome back. Today we're diving into a powerful tool used in data science and machine learning, principal component analysis or PCA. Imagine you have a data set with tons of variables: age, income, spending score, education, and more. It's hard to visualize all of that at once, right? That's where PCA comes in. PCA helps simplify complex data by reducing the number of variables while keeping the most important patterns. It transforms your data into new components that are uncorrelated and ranked by how much variation they capture. So let's start with a simple illustration. In many cases, there are several features or independent variables given, and we need to forecast the label or dependent variable. As discussed before, multicollinearity is always a potential issue in the face of numerous independent variables, and there is normally a need to cut the dimensions to simplify the modeling. For this lesson, however, we'll focus on two independent variables only and one dependent variable to simplify the discussions and show how principal components analysis is done and the intuition behind it. This can always be extended anyway to higher dimension problems. Here in this example, we have independent variables x and y, and we want to predict z, the dependent variable. However, a preliminary analysis of x versus y shows strong correlation, so we're worried about multicollinearity. Intuitively, we consider dropping x or y before regressing versus z. But then, how do we decide that? Well, to help address this issue, let's consider the variance-covariance matrix of x versus y, which contains all the variations between these two datasets. In fact, we can say that since the total variations between x and y are captured by the variance-covariance matrix itself, it would be great if we had a way to assign how much of the variation is attributable to x and how much to y in terms of scalars rather than via a matrix like the variance-covariance matrix itself. So now this transforms the problem into one of converting the covariance matrix into scalars associated with a different axis. And in fact, we can use the magic of linear algebra to do just that. Consider the following equation. AV is equal to lambda V. Here, lambda is called an eigenvalue and V is called an eigenvector. Now, what is the implication of AV equals lambda V? Since multiplying the variance-covariance matrix A by V is the same as multiplying lambda by V, then intuitively, A is represented by lambda. Thus, we are able to transform the covariance matrix into different scalars. If there are n variables, then A is n by n, and there are exactly n eigenvalues or lambdas and n eigenvectors. So it's like A can be folded into n different lambdas such that the sum of all the lambdas or eigenvalues will represent the totality of A. So think of the eigenvalues as representing the total variations measured by A. Working on our example x versus y, we have the covariance matrix shown here. Now for our 2 by 2 matrix, we have two eigenvalues and two eigenvectors. By the way, the focus here will be on the intuition rather than the computation of eigenvalues and eigenvectors. Alright, so we now break down A into the two eigenvalues as follows with their corresponding eigenvectors. Note that we can think of A, therefore, as broken down into two eigenvalues at 2.3069 and 0.24878. That is, we can think of A as being folded into the two eigenvalues, and each eigenvalue is associated with an eigenvector. But what are the eigenvectors exactly? It turns out that for an n by n variance-covariance matrix, the V's are the principal components or axes of the n by n matrix. If there are n variables, then there are n axes that are all perpendicular or orthogonal to each other. So for our 2 by 2 matrix, there are two perpendicular axes. Now for 3 variables or higher number of variables, it's hard to imagine what perpendicular is. And we just need to accept that for higher dimensions, that's exactly what's happening. So here, eigenvectors v1 and v2 define the two principal components that remain invariant no matter how much the vectors get squished or pulled by the eigenvalues. In our example, the eigenvalues expand here by 2.3069 or contract here by 0.24878, the informational content of A along the principal components v1 and v2 respectively. But the axes don't change and just stay put despite the distortions being created by the eigenvalues. In a way, a new set of axes relative to the axis of the original data can be redrawn by rotation such that the data can be projected onto a principal component, with that principal component explaining a percentage of the sum of all eigenvalues. Here, for example, the first principal component explains 90.3% of the total variations, while the second principal component explains just 9.3% of the total variations. This suggests that if we need to drop a variable, we may want to keep x and drop y so that our model can still explain more than 90% of the variations. And that's it, problem solved. Keep x, drop y. In summary, PCA is about finding components that are basically new axes defined by eigenvectors, and then finding out and apportioning explained total variation as captured by the eigenvalues associated with each eigenvector. In doing so, the first principal component captures the most variance, the second captures the next most, and so on. The best part? You can often keep just two or three components and still understand most of what's going on in your data, enabling you to drop variables that don't explain much of the total variation and allowing you to focus on those that do. In this way, you can reduce the dimensionality of your data and of your multiple regression. And before we go, here are two important tips. Tip number one. When doing PCA, it's best to normalize the data for comparability. Otherwise, variables with naturally large metrics will dominate the ones with smaller metrics when paired together for covariances. In this case, using the correlation matrix might be the better option. Tip number two. It's best to work with domain experts regarding variables to drop or combine rather than just using PCA as a black box solution. PCA is more exploratory than anything else. For the final predictive modeling, use multiple regression. Finally, the whole process is as much art as it is science. So yes, bring those domain experts in. PCA is used everywhere. Image compression, genetics, finance, and even to make sense of customer behavior. So if you're working with high-dimensional data and want to visualize or simplify it, give PCA a try. Now smash that like button if you learned something new, and don't forget to subscribe for more analytical tips. We'll give more follow-up lessons on this one in the next episode. See you next time!